Okay, guys. I think everything is in place. Yeah, so last time we were talking about Laplace transforms. The basic idea was to represent signals in the Laplace domain. It helps us solve differential equations, or we can even bypass writing the differential equations and directly go to the circuit and solve the circuit just using functions of S. But we have to have some interpretation for this S. It's basically the Laplace variable. It's a complex number. It's similar to the AC steady state analysis that we did, right? In that case, we had everything was a function of j omega. And we were solving circuits that have forcing functions that were all the same frequency. Whereas here, we can have arbitrary forcing functions, which might come on and off. So this would cover cases of transient analysis as well as AC steady state analysis. So it's a little bit more general. But in order to do the math, you need to understand what a Laplace transform is. It's an integral, right? It's not written here, but we discussed this. So capital F of S equals integral from 0 to infinity of f of t e to the minus st dt. And this S is a complex number. So we calculate this integral for various functions. So here on the left are small f, and on the right are the Laplace transforms. And these Laplace transforms are valid for certain values of complex numbers S. This is not emphasized in our book, but there is also a notion of regional convergence, which means like when you're writing, for example, that this is the Laplace transform of that guy, what value of S are you assuming? I mean, obviously, you cannot be assuming S is equal to minus A, for example, right? That would blow up. Right? So it turns out that S has to have a real part that's bigger than minus A for you to be able to write this down. Anyhow, so that's the Laplace transform. The next issue that we addressed last time, so by the way, in order to get these Laplace transforms, you need to use your basic integration. You can set up these integrals, plug in, for example, this guy for f, and try to carry out this integral, right? Which is going to be an integral from calculus that you thought you should forget, but it's back, right? So it's a polynomial times an exponential. So these are all doable integrals like that. You would find this in the back of your calculus book. The only difference would be that in calculus, you didn't have any complex numbers, but still the rules are the same. So in calculus, S would be a real number, for example. But even if it's a complex number, the integrals are the same. You use integration by parts or whatever. Okay, so that's the Laplace transform. The next issue is, how do you find the inverse Laplace transform? Meaning, if I give you f of S, how do you find the f of t? And of course, one way is that if you have this table and I give you one of these guys on the right, you can find the one on the left. There's nothing to be done. However, if I give you, for example, 2 over s plus 1 minus 3 over s plus 2, right, as your f of s, and I ask you to find f of t, Now what you would do is you would find the inverse Laplace transform of this guy and subtract from that the inverse Laplace transform of this guy, right? And the inverse Laplace transform of the first term, the first term is simply 2 times 1 over s plus 1. And 1 over s plus 1 is this guy with a is equal to 1. So the inverse Laplace transform of this guy would be 2 times e to the minus t. And the inverse Laplace transform of this guy would be 3 times e to the minus 2t, right? So that's simple. You know, in other words, if you have sums of things like this on the left-hand side, you're going to get sums of things like this on the right-hand side. So that's a property of the Laplace transform, which says that you can do term-by-term Laplace transforms if you have a sum of terms, right? For example, if you have a sum of 2 terms like this, its inverse Laplace transform will be the inverse Laplace transform of this minus the inverse Laplace transform of that, right? And the coefficients in front are the same ones that you would get, right? So in other words, instead of 1 over s plus 1, if you have 2 over s plus 1, the 2 is extra, you can pull it out. You find the inverse of 1 over s plus 1 and then multiply it by 2, right? So those are the tricks of the Laplace transform. There are some other, so that's one property, right? There are some other tricks, right? So these are called, so there are 2 kinds of Laplace transform tables. One of them is this one, like actual Laplace transform pairs that have been calculated. Another table is the properties, right? So one property is that if you add time functions, you should add the corresponding Laplace transforms. In other words, the Laplace transform of a sum is the sum of the Laplace transforms, right? But there are other properties, so you can find these in the book. So these are some of the properties, you know, some famous ones. If you multiply the time function by a constant, the Laplace transform gets multiplied by the same constant, right? If you add 2 time functions, you're adding their Laplace transforms. If you subtract 2 time functions, you're subtracting their Laplace transforms. So there are other properties. One famous one that we're going to use is if you differentiate the time function, then this is what you need to do to the Laplace transform, right? It depends on how many derivatives you're taking, but say you're taking just one derivative, right? So if you take one derivative of f of t, meaning n is equal to 1, then maybe I can make it larger. Right? So if you have this situation, but n is equal to 1, then its Laplace transform is going to be, generically it's this, right? So you would get s to the 1 times f of s minus s to the 0 times f of 0, right? ns to the 0 is 1, so you get basically f of 0, right? So the Laplace, we can write basically that d dt f of t is Laplace transform pairs with s f of s minus f of 0, right? We can write that. Which means that if you take the derivative, time derivative of the time function, and then take the Laplace transform, that's equivalent to taking the Laplace transform first, multiplying by s, and subtracting the initial value of f, which is f of 0. Okay? So this double arrow means Laplace transform pair. It doesn't mean equal, right? These cannot be equal. This is a time thing. This is a s thing, right? They are in 2 totally different domains. So we can use this when derivatives pop up, which they do in circuits, differential equations, right? We can use this, and that's something we're going to use also, right? Okay, so there are other properties as well. I won't go through all of them. Okay, and we actually talked a little bit about them last time. So last time we were also in the process of doing this thing, partial fraction expansion. Partial fraction expansion is when you have a ratio of 2 polynomials in S, and you want to basically massage it in a way that you can do term-by-term inverse Laplace transforms. So this is the problem that we solved last time, and I'm just going to quickly So I'm going to explain this by example rather than, because if you try to write the general, if you write the final answer for a mathematician, right? Suppose you're a brilliant mathematician, right? You're a genius, right? But you've never seen inverse Laplace transforms. Then, yeah, I can write it down mathematically in a nice, neat way. It's like perfectly logical, but it's kind of hard to understand. It's better to just run through it by an example, right? So suppose we want to find the inverse Laplace transform of this guy. In other words, we want to find the time function whose Laplace transform is given by this guy, right? So how do you do that? What you need to do is to, if possible, to write it as a sum of terms whose individual Laplace transforms you know. In other words, if I can write this guy, which is this, in this form, meaning a constant divided by the first term in the denominator, plus another constant divided by the second term in the denominator, plus another constant, etc. Right? So if I can write it that way, then I know how to take the inverse Laplace transform of this guy. I know how to take the inverse Laplace transform of that guy, right? Because 1 over s is u of t in the time domain. So this guy would have an inverse Laplace transform of k0 times u of t. So this arrow just means it's the inverse Laplace transform. This guy would have an inverse Laplace transform of k1 times e to the minus 2t u of t, for example, right? So these are Laplace transform pairs, and the k0 and k1, these are just constants. We need to figure them out, right? The point is that the challenge is to basically write this guy in this form. Once you do that, then you go to the table and you use properties of the Laplace transform. So how do we find these constants? Well, we talked about that last time. What we do is the following. So there are many cases. So in case 1, which is what we started talking about, and we did this last time, we did this particular example. So I'm going to go through this kind of quickly. In case 1, all the poles are distinct and real. So in this case, basically, you have a pole of s is equal to 0, s is equal to minus 2, s is equal to minus 4, s is equal to minus 5. We have 4 different poles, right? Which are the values that make the denominator 0. So those are all different from each other. And so in that case, there's a result that says it can be written in this form, right? So if you believe it can be written in this form, meaning what is this form? It's basically a constant, some constant we want to find divided by this, plus another constant we want to find divided by that, etc. Right? If it can be written in that form, then these constants are not hard to find. All you got to do is the following. So if you want to find k0, just multiply everything by s. So you're going to get, so this guy is going to go away. This guy is going to go away. You're going to get s here, s there, and s there, right? And then you plug in s is equal to 0. That's going to wash this guy out, that one out, that one out. So you're going to get k0, right? And then you're going to put s is equal to 0 here as well. So you just get some number there. That will give you k0, right? And that number, I mean, that's easy to do in your head in this case, because it's just 12 times 1 times 3 times divided by 2, 4, and 5, right? So if you do the math, you get some number for k0, right? And that number comes out to be 36 over 40. We did that last time, right? And if you want to find the k1, you do something similar. You multiply everything by s plus 2. S plus 2 here, s plus 2 will cancel, s plus 2 here, s plus 2 here, and this s plus 2 will cancel, right? And then you plug in s is equal to minus 2 to get rid of everything, except this guy. This guy doesn't disappear, right? If you plug in s is equal to minus 2, this will wash, that will wash, that will go away, right? And you plug in s is equal to minus 2, here you're going to get some number, and that number will be equal to your k1, right? So that's how you find k1. So you can find each term like that. And once you find those terms, that's going to be your, that's going to be all the constants that you need. So once you find those constants, basically you have this form, right? K1 came out to be 36 over 40, K2 came out to be 1, K3 was 36 over 8, K4 was minus 32 over 5, right? So they found all the constants. Now they need to find the inverse Laplace of this whole thing. Well, 1 over s is u of t, right? So this is going to be 36 over 40 times u of t. So that's 36 over 40 times u of t, right? They pulled u of t outside. Everything has a u of t in it. 1 over s plus 2 is going to be e to the minus 2t. So whenever you have 1 over s plus a, remember we have this, right? 1 over s plus a is e to the minus at u of t, right? So we have that. So here a is 2, here a is 4, and here a is 5. So, and along with the constants, and when you pull the u of t out, this is the final answer that you get, right? So in an exam situation, I do, it's usually quadratic, right? So we don't even have like 4 poles. So it's, I will give something, like 1 over s plus 1, s plus 3, and find the inverse Laplace of this. Then you have to write this as a over s plus 1 plus b over s plus 3, and then you find a and b, and then this is going to give you a times e to the minus t. This is going to give you b times e to the minus 3t, etc. Right? So with a u of t in front. So the point is, in an exam situation, things will be simpler probably, usually. But I mean, there's a method. So if you follow the method, this class is just a bunch of methods, right? So if you know how to perform the method, you'll do it correctly. It requires arithmetic, complex or real, but it's a straightforward task. Okay, so that's what you have when the poles are distinct and real. Okay, so here's another possibility, which we can talk about. So here they generically described it, where the poles are, suppose you have 2 poles that are complex conjugate pairs. So I mean, let's again start with an example. So suppose we have this situation. So we want to find the inverse Laplace transform of this guy. Okay. And so in this case, what we do is we shamelessly just factor this out. Okay. And we find that it has poles, but they're complex. So one of the poles, and how do I find the poles of this? It's the values of s that make the denominator 0. So s squared plus 4s plus 5 is equal to 0. You use the quadratic equation. So you get minus 4 plus or minus square root 16 minus 25 over 4, right? So that's basically the roots of that guy. So that's a minus, which is a minus 9. So it gives you 20, right? 16 minus b squared minus 4ac. So 4ac is 20. So those are the roots of the denominator of this term, right? So, and what is that? That's minus 4 plus or minus square root of minus 4 divided by 4, right? Square root of minus 4 is 2j. So you get minus 4 plus or minus 2j over 4, right? What did I do? So B. So somebody can check me, hopefully. So I'm just using this formula, right? This is s squared plus 4s plus 5. So this is your b. This is your c. This is your a is equal to 1. So it's minus b plus or minus square root b squared minus 4ac, right? Over 2a. 2a is 2. That's why I was confused. Right? So minus b is minus 4 plus or minus b squared is 16 minus 4ac is 20, right? So and divided by 2a, this should be 2a, is 2, a is 1, right? So you get basically minus 2 plus or minus, so this should be true also, minus 2 plus or minus j, right? Yeah. So those are the values, those are the roots of this guy, right? So I'm just factoring a second order polynomial, right? Nothing, this is something you should know prior to this class. Just because I made a mistake doesn't mean it's not easy, right? So it's, which is sad to say, but true. Okay, so so we just factor this guy, and then we get this, right? Because it has to be the way that you write it is it's because it's minus 2 plus or minus j, so you have to have s minus 2 plus j times s minus 2 minus j, right? Those are in other words, you're subtracting the roots. For example, if the roots were 2 and 3, it would be s minus 2 and s minus 3, right? If roots were negative, then you get s plus 2 and s plus 3. Because it's the value of s. If s is equal to this guy, then you're 0, right? I'm just again explaining high school mathematics here, except there are complex numbers involved. So basically this guy is this one, right? S plus 2 minus j, and this guy is this one, which is s plus 2 plus j, right? So we just factor this thing. Now the question is, how are we going to write it in a way where we can do term by term inverse Laplace transform? We write it as before, right? We do exactly the same things we did before, except we have to deal with complex numbers, right? But once we are done, everything is going to come out real. Once we take the inverse Laplace transform, everything's going to come out real, right? We will see that. So we factor this this guy. Now we are writing this is equal to that, right? The thing we need to be careful about is that you know, we had K1, K2, K3, and K4, right? In our example, K0, K1, K2, K3, they were all different, and they came out different, right? 36 over 40, 1, whatever, and they were real, right? Now, the K values corresponding to the complex poles will be complex numbers, and they will be conjugate pairs, right? So in other words, if this is K1, that's going to come out K1 conjugate. That's just the way it is, right? Now, how do you find the K0, K1, and K1 conjugate, right? That's the issue. By the way, when I say that's just the way it is, this is something you can prove, right? So, in other words, if you, I mean, let's go back to this is going to be a digression, but let's go back to the real example that we did. If you want to check, for example, that this guy is really the original guy, this one, right? That's basically what we did, right? We took this guy, we used a bunch of trickery to write it this way, and then we took it term by term inverse Laplace transform, right? So if you are not convinced that with these constants, you would actually get this back, you can actually do the algebra and multiply stuff out using fractions, right? And how would you multiply this out? This guy needs to get multiplied in the numerator and denominator by all of these guys, right? It's like, I don't know what it's called in English, the equating the denominators. When you add like 1 over 3 plus 1 over 4 plus 1 over 5, what do? You multiply the numerator and denominator there by 4 times 5. You multiply the numerator and denominator here by 3 times 5. Multiply the numerator and denominator here by 3 times 4, right? So you can do that here as well. You multiply everything out here. Multiply this guy with s plus 2 in s plus 4 and s plus 5 in the numerator and the denominator. Multiply this guy by s plus 4 and s plus 5 in the numerator and the denominator, right? For each term, which would not change anything. And then everybody would have the same denominator. You add the numerators, massage the numerator, see if you get this, right? And the claim is yes, you would get it, right? So in other words, you can verify your result is all I'm saying. Once you do all the calculations, you can verify your result with some algebra. I mean, you might not have the time to do that. You might not want to do that, but it's something that's doable. So similarly here, when I say this guy can be written in this form, and that's just the way it is, it's something you can verify. Once we find K0, K1, and K1 conjugate, you can multiply everything out here and combine all these fractions and write it this way. So it's possible to verify. Okay, now how do we find K0, K1, and K1 conjugate? To find K0 is very easy. You just multiply everything out. It's like before. You multiply everything out by S, right? So this S is going to go away. That S is going to go away. I'm using this. This is an equation, right? I'm multiplying both sides by S. So I get an S here and an S there. Substitute S is equal to 0. These guys go away. So I get K0 on the right-hand side, and I get some number on the left-hand side. And that number comes out to be a real number, which is 4. It involves multiplying complex numbers with each other, but they're complex conjugate. And when you multiply a complex number and its conjugate, you get a real positive number, right? So, so the point is K0 is easy to find. It's the same method, nothing different. What about K1 and K1 conjugate? Well, let's find K1. K1 conjugate will just be the complex conjugate of K1, so that's not a problem. Let's find K1. How would you find K1? Well, you just, again, it's the same method, but you need to multiply everything by this guy, right? So you multiply everything out by S plus 2 minus J, right? So I'm going to multiply this guy by S plus 2 minus J. I'm going to multiply this guy by S plus 2 minus J. I'm going to multiply this guy by S plus 2 minus J, which is just going to cancel the denominator. And I'm going to multiply this guy by S plus 2 minus J, right? So that's basically what I'm going to do. So once I do that, on the left-hand side, only this term will wash away. And then what I'm going to do is I'm going to substitute S equals minus 2 plus J, right? If I plug in S is equal to minus 2 plus J, this guy, remember, has S plus 2 minus J, and this guy has also, right? So these guys are going to go to 0. So only K1 will remain. In other words, exactly the same thing as we did before, except the thing we need to multiply with and the number that we need to substitute is going to be complex value. But the trick is the same. You for the value of K that you're interested in, you multiply everything through by the denominator of that. So if you're interested in K1, you multiply everyone through by this, meaning that all the numerators are going to have an additional this term. And this guy is going to have this canceled out. And then you plug in the value of S that makes that term that we multiplied with 0. And then that's just going to cancel everybody. This one's going to get canceled. That one's going to get canceled. You're going to get some number here, and you're going to have only K1 here. So if you do that, you basically, these are the complex numbers you're multiplying. So you're going to get some K1 value, which is going to have a magnitude and a phase. Okay. So that's just complex arithmetic. You substitute S is equal to minus 2 plus J, which is the value that makes the denominator 0 here, right? And that's just the complex arithmetic. You're multiplying stuff in the numerator, dividing by some stuff in the denominator. You take a calculator that can do complex arithmetic. That's going to give you some K1 value. It has real part and imaginary part, or it has a magnitude and phase. Here, magnitude and phase is convenient for us. So that's just K1. Okay, that's K1. And if you, I think we should be past this point, but we can easily verify this, right? So how did they? I think I have this thing open here. So the claim is that it's not this one. The claim is that if you take 10 S plus 2 over S times this thing and substitute S is equal to minus 2 plus J, right? That won't make this guy 0, right? Because this guy is the conjugate of the value that will make it 0. So this will just give you a valid thing. And that's just going to be K1. I mean, let's do that. 10 times S plus 2. So let's set S to be minus 2 plus J, right? S equals minus 2 plus J, right? And then we're going to calculate this ratio. 10 times S plus 2 over S, 10 times S plus 2 divided by S divided by what we had there, which is S plus 2 plus J. S plus 2 plus J, right? So that's going to be a complex number, minus 2 plus, minus 2 minus I, right? So if you look at its magnitude, so let's call that number Z. So if you look at its magnitude, absolute value of Z is 2.23. And if you look at its phase, which in MATLAB is angle of Z, is minus 2.6, but you got to convert that to degrees, because the book has it in degrees. So we need to divide it by 2 pi and multiply it by 360, right? What did I do wrong? I put times divided by. So the n's divided by 2 divided by pi times 360. So that's going to give me the angle, which is minus 153 point something, right? Which is what they have, right? 2.236 with an angle of minus 153 something. So that's K1, right? That's how they found that. And K1 conjugate is the same thing with a phase angle. That's the other side. So since this is negative, that has to be positive, right? Now, why is this useful for us? We can go ahead and do term by term inverse Laplace transform. Now, I can do it for this case, but they did it for a general case up here. So I'll show you how you do it for a general case. So in general, if you have K1 with an angle of theta with this denominator plus K1 with an angle of minus theta, that's the conjugate, with this denominator, what's the inverse Laplace of this, right? How would you find that? So they worked it out here. So I don't want to rewrite everything. So for us, basically the magnitude of K1 for us is 2.2 something. Theta for us is minus 153, right? Alpha for us is 2, right? And beta for us is the value that multiplies minus J, right? Which is 1, right? So let's just do it in the general case here. So in other words, if somebody gives you this as a Laplace transform, right? How would you find the inverse Laplace transform of this? So there are different ways of doing this. This turns out to be a cosine of something with some angle, actually. So let's actually see why. Let me clean this up. So my goal in life now is to take the inverse Laplace transform of a term like this, okay? Which we are doing in our problem as well. But I want to just do it for the general case, where the angle is called theta, and the real part that we're subtracting is called alpha, the imaginary part is called the beta, etc. Right? So how do you do that? You can just plug in directly the formulas that we're familiar with, right? So this guy is of the form K1 e to the j theta, which is just some number, times 1 over s plus a, where a is, what is a? A is just alpha minus j beta, right? So an inverse, so this is just a constant. And the inverse Laplace transform of that is e to the minus at, right? times u of t. So this is so when you find the inverse of this guy, so if you take the inverse of this guy, you're going to get e to the minus at u of t, and then you have this constant in front, so that's the magnitude of k1 e to the j theta, right? So, and a, what is a? A is alpha minus j beta, so you can substitute that if you want, alpha minus j beta, which all multiplies that t, right? So if you plug that in, basically you get this guy. I mean, I can make it larger so you can see. I mean, I guess you have to see everything. Right, so in other words, I took the 1 over s plus something, that something is my a, which here happens to be a complex number, and I just applied that like it was a real number, and basically I get this, right? So that's the first term, and the second term is exactly the same thing with the conjugate. So you're basically going to get the constant that you're multiplying, instead of being this guy, which matches that one, now the constant you're going to multiply is going to be this guy, which has a minus theta, which matches that one, right? And as far as the exponent, instead of having e to the minus at, you're going to have e to the minus the conjugate of at, right? So so you're going to get, instead of having alpha minus j beta, you're going to get alpha plus j beta, okay? It looks like a mess, but the beauty of this is that we can separate the real and the imaginary. So here, I mean, let's look at this a little. So this is what we want to simplify now. This is the guy we want to simplify. Let's remember here that magnitude of K1 is just a positive real number. We can just pull that out of everybody, okay? And then e to the minus alpha t is also in both terms. E to the minus alpha t is in both terms. So I can pull that out as well, right? And that's just a decaying exponential like you've learned in high school, right? So there's no problem with that. And then you have a sum of two complex exponentials. You have e to the, once you pull out the alpha, you end up with the, you combine all the terms that have the j in the exponents, right? So you get, if you take this guy and combine it with that guy, that's going to give you this one. And if you take this guy and combine it with this one, that's going to give you that one. And that's exactly of the form e to the j something plus e to the minus j of that thing, right? But we know that that's some form of a cosine. Cosine is e to the jx plus e to the minus jx over 2, right? Here the over 2 is missing. There's no, so we get an extra factor of 2, basically, right? In other words, if you were to use this formula to write the cosine, this cosine, it would be, this would be two complex exponentials, which could be put in this form, which could be back put in the form that we originally had. If you ever have something of the form e to the jx plus e to the minus jx, that's cosine of that thing, okay? Times maybe some constant, maybe 2 times that, right? So that's why we have the 2. That's basically this term. In other words, I can put the 2 here. 2 cosine is e to the jx plus e to the minus jx, right? So the bottom line is that we basically use the single exponential inverse Laplace transform formula twice, and we keep track of the complex numbers and their conjugates, and we use this basic cosine identity that relates it to complex exponentials, and we're able to write the inverse Laplace transform as e to the a decaying exponential, a real decaying exponential times a sinusoid, basically, right? Where everything is now real. The final answer is real, right? So that's a way to do it. Again, for a first course, this is doable, but I like to just ask simple questions, so I stick with real numbers usually. But it's good to know how to do this. I mean, another way to think about this, by the way, is you might say, well, this is e to the minus something t cosine something t, right? So so we had that in our table. Actually, maybe it wasn't my other. It was over here. There's my table. if you look at this table, right, e to the minus something t times cosine something t, right? So we have this in our table. In other words, if you were to take the expression that we ended up with and massage it and try to put it in this form, then maybe you could use this inverse transform as well, and you could totally avoid complex numbers, right? So that's also possible to do. But I think using complex numbers is effective because basically you just treat the complex numbers like they're real numbers, and then you just do complex arithmetic, simplify everything, and the final answer for the time function, the inverse Laplace transform, just comes out to be real value, right? So I don't know where I'm going with that. Let's go back to the. So we covered case 2. Case 2 is when we have poles that are complex value. Okay. And in case 3, which is also kind of hairy, even maybe more hairy than the other two, is when you have powers of s plus something in the denominator, or even powers of s, like if you have s cubed in the denominator or s plus 1 cubed in the denominator, right? So let's do that case. Again, as usual, I want to do it through an example, because I think the example illustrates the point. And also, we need to believe what kind of representation is necessary. We need to understand that. So suppose we have a situation like this, where you have just a regular old transfer function, except you have a s plus 1 cubed in the denominator, right? I don't know if that's visible to you guys. I'll make it a little bit larger. You have s plus 1 cubed in the denominator. So, so the first question is, what is the general form of this thing? And the answer is a little bit different than before. The answer is that you're going to get constants divided by, so for example, if you have s plus 1 cubed, you're going to get k11 over s plus 1 plus k12 over s plus 1 squared plus k13 over s plus 1 cubed plus k2 over s plus 2, right? So in other words, you always have a constant divided by a power of the term that has a power that's bigger than 1. And then you have a constant divided by the other term, right? So, and if there were other terms, for example, if there was a s plus 3 here, then here you would have plus k3 divided by s plus 3 here, right? So we don't have that, but so the point is that you have a constant divided by the first power of s plus 1, which is the term that has 3 powers here, and then the second power as another constant, and then third power as another constant. Okay. So now the question is, so if you believe this, if you believe that this can be written in this form, and we can again check it. Once we find the numbers, we can go back and do fractional arithmetic and put this in that form, right? So in other words, we can verify that. So let's believe that, so that it can be written in this form. Then how do you find these constants? Again, the usual question. We're going to use a similar trick, but there is going to be some differentiations involved, which is the part that's a little bit tricky. It's not tricky, but it's not something we've seen so far. So let's talk about it. So let's first find the k13. By the way, why are they indexed this way? Because we view the k11, k12, and k13 as constants having to do with this term. So that's why they get the, so that's why we don't call them k1, k2, k3, and then this one k4, right? But there's nothing wrong with that or right with that. It's just a notational choice, right? I could have just called them A, B, C, D, right? That's fine as well. But the reason they both have the same first subscript, k1 something, is because they all have to do with this term. They are all byproducts, all evil that flows out of the fact that this power is bigger than 1, right? Okay, so now how do you find the, so if this is really equal to that, how would you find k13? K13 is the easy one. What you do is you multiply everything by s plus 1 cubed, right? So if I multiply everything by s plus 1 cubed, this guy will go away, this guy will go away, and I'll end up with s plus 1 squared. This guy will go away, and I'll end up with s plus 1. This guy will go away, and I'll end up with this. And this guy will give me s plus 1 cubed, right? Now I substitute s is equal to minus 1, right? If I substitute s is equal to minus 1, I get some number for this. This is a number which I can calculate. S is equal to minus 1. I'll let you do that. 10 times minus 1 plus 3, which is 2, divided by minus 1 plus 2, which is 1. So that's 20, right? So this number will be 20. And if you plug in s is equal to minus 1, this guy will become 0. This guy will become 0. This guy, nothing will happen to it. That's just a constant. And this guy will become 0. So K13 will be 20, right? So that's easy. That's similar to what we've done, right? Now, things get a little bit more hairy when you have to deal with when you want to find the other constants. So let's try to find, for example, K12. We found K13. Let's find K12. So it's claimed here that if you want to find K12, multiply everything by s plus 1 cubed, and then take some derivative. It's it's kind of mysterious. Why are we taking derivatives here? But it will become clear when we actually write everything out, which I already did for you guys here, right? So let's take the equality that we had here, the original equality, before we multiplied it with anything or substitute anything, right? So we take that equality, and that equality is written here in red in the bottom, right? You have 10 times s plus 3, s plus 1 cubed. So I'm multiplying everything again by s plus 1 cubed. So this guy is going to go away. And then I'm going to end up with this guy going away and this guy having s plus 1 squared. This guy going away and this guy having s plus 1, right? So I have that here. And this guy is going to have just K13. And this guy is going to have s plus 1 cubed. And then I have some denominator for that, right? Okay, that's fine. Now, what's my goal in life? My goal in life is to hone in on K12, right? I want K12. How do I get K12? Well, how I'm going to get it is, first, I'm going to differentiate everything with respect to s. That will definitely reduce this guy into just K12, right? Everyone can agree with that, because this guy is just K12 times s plus K12. So if I differentiate everything with respect to s, I'm just going to get K12 plus 0, right? So this guy will serve, K12 will survive out of differentiating everything, right? Of course, if I have to differentiate one term, I have to differentiate every term, right? I have to differentiate the left-hand side, the right-hand side, every term on the right-hand side. So what I do is I take one derivative of everything, right? So I take one derivative of this nonsense, which is just a calculus derivative, right? Numerator, denominator, you know how to do that. Derivative of the numerator times the denominator minus derivative of the denominator times the numerator, or vice versa, I can't remember. Divide by the square of the denominator, right? This is the quotient rule for differentiation, right? So you do that here and substitute s is equal to minus 1. And here, you're going to differentiate this guy with respect to s. That's just going to give you K12 when you take one derivative. This guy is going to totally disappear, right? When you differentiate this guy with respect to s, what are you going to get? You're going to get 2 times s plus 1, right? But later we're going to substitute s is equal to minus 1. So this guy is going to disappear. And this guy is also going to have some, if you use the quotient rule, in the numerator, you're going to end up with a bunch of s plus 1s, which are going to disappear when you substitute s is equal to minus 1. In other words, differentiating everything once basically amounts to killing everything except the constant in front of the s plus 1 term. Okay? So that will help me solve for K12, right? Because on the left-hand side, I'm going to end up with a number, right? So what are the steps? I take the original thing that I had, which is this guy, multiply everything by s plus 1 cubed, which is this guy. I take the derivative with respect to s once, and then I substitute s is equal to -1. That's going to give me a number on the left-hand side, and that number is equal to the only term on the right-hand side that survives, which is basically this guy. Everything else doesn't survive, either the differentiation, because it was a constant like this one, or because it has too many s plus 1s in it. When I substitute s plus 1, s is equal to -1, it gets canceled out, right? Because I'm doing two operations, differentiation first, and then substituting s is equal to -1. So it's a trick to solve for that unknown, right? So that's what you do if you want to find the term K12, which originally had a s plus 1 square, right? It originally had a s plus 1 square. So you can find K12 by doing all these tricks. Now, if you want to find the other terms, for example, K11, right? Then you have to what do you need to do? You do exactly what we did here, except you differentiate twice, right? When you differentiate twice, so in other words, these are the steps. You take this guy, multiply it by s plus 1 cubed, which gives you the red on the left-hand side here, right? Which gives you the red on the left-hand side here, which is what we did before. And then you take, and you do the same thing on the right-hand side, multiply it by s plus 1 cubed. So you're going to get a bunch of s plus 1s or some constants, right? And then you take two derivatives, because I'm now interested in K11. When you take two derivatives, so let's write that. So this is going to be d squared ds squared. So this is a new, now I'm not solving for K12, I'm solving for sorry, I'm not solving for K13. I'm solving, what am I doing? I'm solving for K11, right? I'm trying to solve for this guy. So maybe I can write it on a separate place so things don't get mixed up. Because if I'm confusing myself, you're probably confusing you guys. So what you would do is, maybe I can write here, d squared ds squared of 10 s plus 3 over s plus 2. Well, after I take the derivative, I'm going to substitute s is equal to -1. And on the right-hand side, I'm going to do d squared ds squared of all the stuff that I have here. K1, 1 s plus 1 squared plus K12 s plus 1 plus K13 plus K2 s plus 1 cubed over s plus 2. And then I substitute s is equal to -1, right? So this over here is just a number. And the reason I took two derivatives is because I want to preserve K11, right? If I take two derivatives on this, what do I get? I get 2s plus 1, and then I get 2, right? So I'm going to get 2K11 out of this, right? 2K11, right? This one, if I take two derivatives, it's going to die. It annihilated. This guy is a constant. Even one derivative will kill it. And this guy, if I take two derivatives, it's still going to have some s plus 1 in the numerator, even with the quotient rule. And when I substitute s is equal to -1, it's going to wash away, right? So the only thing that's going to survive on the right-hand side is 2K1. And on the left-hand side, it's just some number I can compute. So I have 2K1 equals some number, and I can solve for K1, like K11. So that's basically the reason we're taking derivatives. We're reducing the order, right? So that's the trick when you have repeated poles. Okay. Now, when you have repeated poles, and when you actually substitute the numbers that you calculated, you get something like this. You know, K11 divided by s plus 1 plus K12 divided by s plus 2 squared. So K12 was -10, because there's a minus here as well, right? Etc. So you write that out. So now you need to take the inverse Laplace transform of that. The inverse Laplace transform of this is 10 times e to the minus t, u of t, right? E to the minus t, because you have -1 as a pole. So that's the minus t. If this was minus if it was plus 2 here in the denominator, you would have e to the minus 2t, right? So this is 10. So in other words, this guy corresponds to this one. This guy is going to correspond to that one. So every time you square something in the denominator, if you look at the table, you need to multiply by t, right? So that's a property that you can look at. Maybe I can quickly show you, because we didn't really discuss that in detail. But if you multiply, by not as a property, but let's look at the Laplace transform pairs, which is here. So if you look at basically 1 over, what's our situation? 1 over s plus a to some power, right? For us, a was, I think, plus 1, right? The power was is going to be either 1, 2, or 3 for us, right? We have separate terms for each. So so you use this formula, right? Okay, so so basically you get t to the some power e to the minus at, basically, and this is just some constant, right? T to the some power e to the minus at will be something of the form 1 over s plus a to some power, right? So I mean, that's another thing that I like to say, like when I teach signals and systems, I like to emphasize like how much a human brain can hold, and mine is not a particularly good one. The point being that, I teach this every year, in different contexts, in circuits and signals and systems, and I still don't know, what is the inverse Laplace transform of something like this, 1 over s plus a to some power. I just know it's t to some power e to the minus at with some constant in front, right? So I can't remember that's n factorial. I could try to derive it, right, from scratch or whatever, but the point I'm trying to make is that, how much, how much are you supposed to memorize? How much should be on your cheat sheet? And how much should you actually be able to derive and know by heart, right? So it's a balance between these things. It's like arithmetic, right? So it's if you were teaching someone arithmetic and they were really concerned with the fact that you asked them to remember the multiplication table, you would say, well, it's going to come handy. Even if you have a calculator, it's going to come handy, right? To know some of the structures, right? So even if you have this table, it's just nice to know that 1 over s plus a is always e to the minus at times u of t. There's a u of t here as well. I think they're assuming t is always non-negative here. That's why they ignore the u of t. But there should be a times u of t here. So the point I'm trying to make is that it's nice to be slightly familiarized with this table. And how do you get familiarized? You do the homework before you copy it from your friends, right? Or at least you attempt it. You think about it so that some of it gets synced in, right? Okay, so all right. So going back to what we were talking about. So basically, you have powers of t for each additional term, and this last one is just 10 times e to the minus 2t. That corresponds to this one. That's not a power of anything. Okay, so that's basically how you do partial fraction expansion, and then do term by term inverse Laplace transform. Okay, now what's the next? So I have like 15 minutes, and I do want to talk a little bit about how we're going to use these Laplace transforms. So let's. I don't know if this is the next one that comes. So these slides are a little bit redundant. I do want to talk about. So yeah, I mean, let's talk about differential equations a little bit. And I think that's this, right? And maybe some other properties of the Laplace transform. So here they are talking about solving differential equations using the Laplace transform. And especially if you're not an electrical engineer, major, you'll probably appreciate this more because when, as electrical engineers, learning about the Laplace transform in a circuits course we will never need to really write a differential equation because there are ways of actually writing some equations in terms of these capital letters that avoid any writing of any differential equation, just like we did with AC steady state analysis, right? There we had phasors and we didn't write any differential equations, even though all of those circuits, if you were to write, loop in the time domain, if you were to write loop equations and node equations, they all simplify into differential, or simplify in quotes, into differential equations. So the point I'm trying to make is that there are ways of bypassing writing of differential equations if your purpose is to solve a circuit. But if you want to appreciate Laplace transforms and you want to forever forget circuits, because maybe you're graduating and you never want to look at a circuit ever in your life again, you're some other major, you would still appreciate the Laplace transform because you want to solve differential equations, because what engineer doesn't, right? So I mean that's the fundamental thing, differential equations for engineers. So having said all that, so here's the Laplace transform of the derivative. So this is the formula that we wrote. Remember we had this formula, we called it f of t before. Laplace transform of a derivative, right? So it's the s. So we had f, small f for this one, and we had a capital F for this one, and we had a small f for that one, right? So, but that's basically the Laplace transform of a derivative, right? And if you repeatedly apply that formula, right? So if differentiating with respect to time means multiplying the Laplace transform with a with s and then subtracting the initial value, you can apply that twice, right? You can differentiate, in other words, differentiating this guy twice means differentiating once and then differentiating it again, right? So if you differentiate it once, you're multiplying. So in other words, we have dy of t dt is Laplace transform pairs with sy of s minus y of 0. That's basically this equation. Instead of x, we have y. And then if you want to differentiate again, what do you need to do? You need to take the Laplace transform of this one. So if you want this guy, d squared y of t dt squared, what should go there, right? So what did we do on the left-hand side? We took a derivative. So on the right-hand side, we need to multiply by s. We need to multiply this guy by s, and then subtract the initial value of the thing whose first derivative we're finding, right? In other words, you need to multiply this by s. What is that going to give you? S squared y of s minus sy0. And then you need to subtract the initial value of the thing whose first derivative you're taking. Here we're taking two derivatives, so we're taking the first derivative of the derivative. So you need to subtract the dy of 0 dt. All I'm trying to explain is that if you have this formula, you can get this formula from it, right? It's a little bit twisted, but and you can use induction to do it n times, in which case basically you're going to end up with like s to the n y of s, and then subtract a bunch of powers of s with some initial conditions and derivatives. So anyhow, we can just believe this formula if that's not convincing. So that's the second derivative. Okay. Now, so we can convert differential equations into algebraic equations. Why? Because whenever you have a derivative, we can take Laplace transforms of everything. So we're going to just get functions of s everywhere. And initial conditions are automatically included, right? So in other words, this is usually for situations where your initial, it's not for cases where things have been running since time immemorial. In other words, there's a start time, right? So usually that's called 0, t is equal to 0. So let's do it the simplest example on Earth. Here's a first order differential equation with an initial condition, which is a constant, right? And if you take in differential equations, we know the answer is decaying exponential. But how would you use Laplace transforms to solve this? You would take the, let's call the Laplace transform of VC of t, VC of s. Okay, that's just our terminology. And so if you want to take the Laplace transform of this guy, what is that going to be? It's going to be the Laplace transform of this plus the Laplace transform of that. So what I want to do is I want to solve this equation, right? So I want to take the Laplace transform of the first one, the actual differential equation, and that requires me to take the Laplace transform of the left-hand side and the Laplace transform of the right-hand side, right? Laplace transform of the left-hand side, which is this, is just it's called this. It's the Laplace transform of the left-hand side, right? And what is that? That's the Laplace transform of the first derivative plus the Laplace transform of VC of t itself. The Laplace transform of the first derivative is this formula, right? Instead of x, we have VC now. So you have s VC of s minus VC of 0, right? That's the Laplace transform of this guy, right? And the Laplace transform of this one is just VC of s, right? So if you, so that's just the Laplace transform of the left-hand side. What's the Laplace transform of the right-hand side? 0. Laplace transform of 0 is 0, right? We didn't really say that, but it's true because if you multiply any function, so if you have Laplace transform of f of t times alpha is equal to alpha times f of s, we said, right? If you take the Laplace transform, so this is a new notation, right? Instead of writing alpha f of t, double arrow, alpha f of s, I'm writing it this way. I'm writing it as, I put an equal sign now, and it's now valid because it means the Laplace transform of what's in the braces is what's on the right-hand side, right? So that's the terminology they're using here. I'm digressing, like I'm on my second digression, but let me actually try to make my point. The point is that the Laplace transform of this one is this one, right? In other words, if I multiply the time function by alpha, I need to multiply the Laplace transform by alpha. And if alpha is 0, guess what? You're going to get 0 here and 0 there. So then Laplace transform of 0 is 0, right? So we should not, I mean, that's what you would have thought anyway, right? So if I were to say in the exam, Laplace transform of 0 is 0, everybody would say yes. So that's why it's not on the exam. So it's not, you're not surprised by that, but you can actually prove it. So this is the Laplace transform of the left-hand side. That's the Laplace transform of the right-hand side. Now we have this equation. Now we can solve for VC of s, just like it's an algebraic equation as a function of s, right? Group the VC of s. So you get s times s plus 1 times VC of s equals V0, right? And then solve for VC of s, you get V0 over s plus 1, right? So VC of s is V0 over s plus 1. So what is VC of t then? Well, this is a constant times 1 over s plus a, right? So it's e to the minus at, e to the minus t, times constant, V0. So the answer is V0 times e to the minus t. And this is valid when t is positive, right? So we're all, when we're dealing with these univariate, not univariate, unilateral, as it's called, Laplace transforms, meaning the integration is from 0 to infinity. We didn't see any other kind actually in this class, but there's another kind that starts from minus infinity, which is called the bilateral Laplace transform. We're always assuming that time starts at 0, right? There is nothing is going, it's like a Big Bang, right? Nothing happened before t is equal to 0, right? T is equal to 0 is the beginning of everything. So the point I'm trying to make is that they didn't bother writing t positive, but t is really positive. In other words, do not try to plug in negative values of t here. If you plug in, let's say t is equal to minus 15, you'll get e to the plus 15, right? Which would be a large number and wouldn't make sense. So t is positive here is my point. But what did we do here? I mean, we solved the world's simplest differential equation using Laplace transforms. And I'm sure you've done this in your differential equation class. And you can do this for second order as well, right? If you have a second order, you'll end up with some constant divided by some second order polynomial, which you can factor and use partial fraction expansion, and then take term by term inverse Laplace transforms. Okay. Now, another one final property of the Laplace transform that I want to emphasize here are called the initial and the final value theorems of the Laplace transform. Okay, they're very simple, except you got to be careful about where the limits are going. Here are the two theorems. This one is called the initial value theorem, because we live in the time domain, right? We are time people, you know, we have watches. So the Laplace domain is a weird land. It's an alien land to us. So when we're talking about initial value, we're talking about t being at its initial time, which is 0, right? So, so initial value theorem is about limit as t goes to 0, what f of t is doing, right? And the final value is limit as t goes to infinity, what f of t is doing. And it turns out that if you know the Laplace transform of f of t, you can find this limit and this limit just by massaging the Laplace transform of Laplace transform of f of t, which is f of s. And this is how you do it. You multiply f of s with s in both cases, but you do something backwards. If you want the initial value, initial time value, you send s to infinity. And if you want the final time value, you send s to 0, right? And we can easily verify these. We can easily verify these. These are facts that can be proven, right? So for example, what is the initial value of VC of t? We found VC of t to be, what was VC of t? It was this guy. So its initial value, t is equal to 0, you should get V0, right? V0 times e to the 1, right? VC of 0 is V0. So initial value should be V0, right? Can we see that from the Laplace transform? This is the Laplace transform, remember, is 1 over s plus 1 times V0. This was our VC of s, right? So if you want your VC of 0, you take your VC of s, you multiply it by s, right? And then you get this guy times V0. And then you send s to infinity. What happens when you send s to infinity with this one? Is you get infinity over infinity, but it's basically 1, right? Because this 1 washes out. So you get 1 over 1. But you can use L'Hopital's rule if you're not comfortable, right? L'Hopital's on that, you get 1 over 1. So you get 1. But you have a V0 you're multiplying with, so the answer is V0. So the initial value is V0, as it should be, right? You can check and verify. And the final value, what about the final value of VC of t? Well, this is a decaying exponential, right? Remember, VC of t itself was e to the minus t times V0, right? So as t goes to infinity, this guy is going to go to 0. So the answer should be 0, right? If I gave you VC of t, you would find the final answer. But the goal here, using the final value theorem, we're going to use the Laplace transform. Laplace transform, again, is VC of s itself without the s is just V0 over s plus 1. So when multiplying with s, you get this. And then you send s is equal to 0, right? You send s to 0. If you want the t is equal to infinity, you send s to 0. It's backwards, right? And so when you substitute s is equal to 0, you get 0 in the numerator, 1 in the denominator, 0 over 1 is 0, answer is 0. As it should be, because our final value was 0, right? So this is nice, because it tells you what the initial value is, it tells you what the final value is. And remember, these are useful for us when we do transient analysis. Initial value, final value, right? So, so these are handy for us, and we're going to use these. So I'm out of time, but I mean, just one more second. If you are still in doubt about the initial and final value theorems, you can easily test your ability to do basic limits from calculus by using these Laplace transform pairs, right? For example, I mean, this is a rather difficult one, e to the minus, it's not difficult, e to the minus at sine b of t. Its initial value would be when t is equal to 0, e to the minus 0 is 1, sine 0 is 0, so you get 0 on the left, right? And if you want the initial value from the Laplace transform, multiply everything by s and send s to infinity, right? So you get bs in the numerator, right? And some second order in the denominator, right? So, but you're sending s to infinity, so you get s to the 1 in the numerator, s squared in the denominator. So the denominator dominates the numerator, so you're going to get 0 basically. But if you're not convinced by that, again, you can use L'Hopital's rule. In other words, if you want to find the initial value of this guy, you would multiply this guy by s and send s to infinity and use L'Hopital's rule. And you would get 0. The answer would be 0, as you can easily verify by plugging in t is equal to 0 to this. And you can do that with each and every one of these, and those are all fair game. You know, to calculus, these are simple limits to calculate. Everybody should know L'Hopital's rule, right? Okay, so I mean, I'm done. Thank you, guys. Next time we'll solve some circuits, and happy Thanksgiving. See you in a week. I don't know if I recorded this one. I don't think. I know I did record it. Thank you.